cs407 Numerical Analysis, Section 6.3, A Brief History of B-Splines. In this section we'll take a look at the brief history of B-Splines and an overview of their uses. This is one of the optional sections of the core material from the textbook. I'll spend quite a bit of time on the theory and on the code, but I won't spend as much time on the forms of the actual equations. I also offer my apologies to Stephen Hawking for shamelessly borrowing the name of his famous text, A Brief History of Time. So, B-splines are special spline functions that are well adapted to numerical tasks and are being used more and more frequently in production-type systems for approximating data. B-splines were so named because they form a basis for the set of all splines. They're sometimes called bell splines because of their characteristic bell shape. Since they're used in production systems, you'll often see implementations of them in library code for interpolating data. So we'll start with the B-spline of degree 0, and this is noted as B of subscript I superscript 0, and that's defined to be 1 if x is between ti and ti plus 1, and 0 otherwise. And basically what these look like is they look a lot like the step functions that you've probably seen in hardware-based classes. Now obviously this function b sub I 0 is discontinuous. However, it is continuous from the right at all points, even where the jump occurs. And since it's a piecewise constant function, it's a spline of degree 0. Any spline of degree 0 that is continuous from the right and is based on the knots described in the equation can be expressed as a linear combination of the b-splines b sub I 0. With the functions b sub I 0 as a starting point, we can now generate all higher degree b-splines by a simple recursive definition. Well, relatively simple. Higher degree b-splines are defined recursively as b sub I k of x is equal to a multiple of b sub I k to minus 1 of x plus a multiple of b sub I plus 1 k minus 1 of x, where k runs between 1 and 2 all the way up to infinity, and I is plus or minus 1, plus or minus 2, etc. And there are some properties. Basically, if x is not a member of, if you're evaluating x and it's not a member of the interval tik plus 1, then the b sub ik, the b-spline at that point, is going to be 0. And otherwise, if it is a member of that open interval, it's going to be some value that is greater than 0. So an efficient method to evaluate a function of the form f of x is equal to the sum of cik bik of x is to use the following formula down here for c sub I. You can also calculate the derivative of b-splines, and you can integrate them as demonstrated in the lower bullet point. But what we're really here for is how to interpolate them. So the past several slides have looked at a lot of properties of b-splines, but we really want to know how to use them in this course. So a basic question is, how do you determine the coefficients in this expression? S of x, piecewise function, approximating it, is equal to, approximating the function you're trying to graph, is equal to the sum, I goes from minus infinity to infinity, capital A sub I, and then the b-splines, bi minus k 2 of x. And we want it so the resulting spline function interpolates a prescribed table such as the one that we have drawn below. Well, for lower degree splines such as bi1, these are the level 1 splines. We'll get an interpolation, or degree 1 splines. We'll get an interpolation that looks a lot like the following, what you see at the bottom. Now this is the chapeau, or the hat-shaped function for the individual b-splines. Now this isn't aesthetically pleasing in and of itself, and this example corresponds to an entry with 4, or a table with 4 entries. And working with b-splines of degree 1, we will get some function that is very choppy, but does begin to approximate the individual values at the knots of the table. What we want is, we would like a higher degree spline, and here the choice of coefficients can be a bit arbitrary. In fact, none of the coefficients is uniquely determined by the interpolation conditions. This fact can actually be advantageous for us if there are other properties that are desired of the solution. And in the quadratic case, we can begin with the equation found under the second bullet point here and impose interpolation conditions, so we end up with a system of equations. And here is our system of equations for j between 0 and n. Now, what we get here is a system of n plus 1 linear equations and n plus 2 unknowns. And those unknowns are a0, a1 through an. Now, basically, again, we have n plus 1 linear equations and n plus 2 unknowns from the formula that we've repeated here at the top. Now, one way to solve this system is to assign any value to a0, and then we have n plus 1 linear equations and n plus 2 unknowns, or n plus 1 unknowns, so they're equal, so it should be possible to solve them. And then we can compute a1 through an recursively using this formula. If you look at the top of page 288 of the 7th edition, you'll see the precise format for these equations and how complicated they can actually be when you get down to the nitty-gritty details. This is one of the reasons we have computers, and we're going to take full advantage of that fact in constructing the pseudocode for calculating these B-splines in terms of their coefficients and the evaluation of the B-spline at a particular x value. So let's take a look at that pseudocode. So what we have here is the B-spline 2 coefficient function, and this is a procedure that computes coefficients a0, a1, an plus 1 in the manner that we outlined previously, basically working with those formulas that can be found on page 288 of the textbook in explicit detail, and on the previous slide in somewhat less detail. So what's important to look at here, you can see the calculations that get done in the main for loop. Here are the initial assignments of the variables, and then we do the initial calculation of those variables, assign a0, and then assign a1 based on the recursive formula, a2 based on the recursive formula, etc. Now, in terms of the calling sequence, ti is going to be the array of size n. That's going to be the not array, the points at which we have defined the function. Y sub I is an array of size n that holds the abscissa points, the values of the function assigned at the points t sub I. And a sub I is the array of n size n plus 1 that holds the ai coefficients in our solution to the equation. And h sub I is an array of size n plus 1 that holds the difference between two individual points in the t table. So, for example, t2 minus t1. And in general, ti minus ti minus 1. So only n, ti, and yi are needed as input values. So they are available and unchanged when the routine is finished. The arrays ai and hi are computed and are available as output after the routine finishes. So next we need some pseudocode to compute the values of the quadratic spline at various points x. So here's the code for that. Now, this function evaluates the value of the spline function that we computed in B-spline 2 coefficient procedure. Its calling sequence has pretty much the same variables in addition to a value x that is a single double value. And basically it's a single real number that will reside somewhere between t0 and tn, where we want to evaluate the spline function. And what this will return is it will return the evaluation of the spline function at that point x. And this actually works pretty well. The authors run this routine on using the table of 20 points that is given as an example in section 6.2, and they get pretty good results, as you can see over on the left. On the left you see the quadratic interpolating spline from this section, and on the right you see the natural cubic spline from section 6.2. And both of them look pretty good as a graph of the curve. You can also accomplish similar tasks using mathematical software, and this is an example from Wolfram's Mathematica software. Here is a B-spline curve and its control points in 2D. What you do is you do the input of the points and their evaluation at those points, and you have the math software graph the B-spline curve at those points. here we're going to have this curve in kind of a dark blue, and the first degree spline function in green between those individual points, and the points are in red. And so this defines the output, and you can see here that the B-spline actually gives a pretty aesthetically pleasing curve compared to the first degree spline function. Some other results in the section. Schoenberg's process. This is an efficient process to obtain B-spline approximations to a given function, and its quadratic version is defined by s of x is equal to the sum from I equals minus infinity to infinity of f evaluated at tau sub I bi2, so the quadratic version of the B-spline. And the tau sub I are basically the halfway points between the knots, and that's where we're evaluating the function f in order to get a more efficient result. Another technique that's similar are Bezier curves, and these are used in computer-aided design for producing a curve that goes through or near to a large number of control points, or a curve that can be manipulated easily to give a desired shape. Now these Bezier curves use Bernstein polynomials, and these were discovered in 1912 by Sergei Natanovich Bernstein, not Erica Bernstein from our math department. You can find out the general form of these on page 292 if you're interested in taking a look at it. So the figure on the left is a graph of the first few of these polynomials, particularly where n is equal to 7 and I is 0, 1, and 5. And you can see these actually produce fairly smooth curves. The closed curve on the right is drawn with these Bezier curves using control points. And this can be done in mathematical programs such as Mathematica, Maple, and MATLAB. So coming attractions: 1, review for the test, 2, the test, and 3, initial value problems. We'll probably do them in that order, and in particular when we get to these initial value problems, we'll see how not to make bridges in the next chapter.